Great. Thanks, Tanya. And hopefully people can't hear the rain too loud outside since whatever this tropical storm thing is on top of us right now. But I think Tanya gave a good intro to some of the background of the Dune Response Tool. It's actually not a tool that's had a lot of funding in recent years, but hopefully I'll demonstrate today that despite that, we're making some interesting advancements with it, and I'll sort of finish on next steps and possible funding sources for that. So as the talk title here introduces, I actually try to go into both deterministic simulations and also probabilistic simulations using this reduced complexity model that I'll mention in a minute. And I should also note that Dylan, who I think is on the line, is a major contributor to all this work. So Tanya already motivated the fact that dunes are important, that we know research has to be done in terms of understanding their resilient services, and that both Aeolian processes and wave-driven processes contribute to their evolution. Not surprisingly, when people want to implement dunes into real world projects, we also need to have some level of design tools or tools to inform the feasibility of those features embedded in real world landscapes and the services that they provide. So not surprisingly, today my talk's going to be about the tools that factor in to whether dunes are feasible design features along our nation's coastlines, and trying to upscale our predictive capabilities to longer timescales for dune evolution. As Tanya noted before, we've really sort of taken two different directions with developing tools in-house within ERDIC related to dune evolution, particularly in terms of the accretional capabilities of dunes. We've done a lot of investment in the Aeolus model. People have probably heard me talk about that pretty extensively. I'll have a couple more slides in a minute just to mention Aeolus if people aren't familiar with it. But we can think about this as a tool that's built in a modular way where we can add a lot of different details. And when it comes to dune systems, a lot of details matter. The type of vegetation might matter, the density of vegetation, details of what the grain size looks like, whether people want to put in sand fences or interactions between the marine environment and the Aeolian environment. And so for real world systems where we want to get to like real design, understanding what details matter in terms of feedback to the system, we've really been putting a lot of effort into this Aeolus model for higher fidelity simulations. However, at the same time, we also want to create tools that are easy to use, that don't have a lot of user inputs, that might be able to give answers in seconds instead of hours to days, and have a lot less needs in terms of data inputs to get going. And so this has really been the motivation of this Dune Response Tool in terms of, let's say, lower fidelity details, but that can still provide information that's useful for long-term planning or rapid assessments, and perhaps to some degree for design or other considerations, because I think there's some gray area in the middle, and that's something that we're still learning, where that trade-off is between these different tools. One thing that I'll note is that in models like Aeolus, and this really applies to any process, truly process-based morphological model, that we really sort of start with the fundamentals and want to understand drivers of gradients of sediment transport at sub-meter scales, and oftentimes upscaling these processes to much longer timeframes or much bigger scales, we run into hurdles. And so the Dune Response Tool is more of an empirical analytical model. So it doesn't necessarily suffer from some of those compounding feedbacks, but it also means that there's fewer details included within the model. So just a little bit of background on Aeolus, just to once again sort of separate the utility of these two different tools that we've been developing in CIRP and across some of the ERDIC R&D programs. This is actually a model simulation, just schematized in Blender, to show some of the more complicated things that we can simulate with a more complex 2D Aeolian transport morphological model. So in this case, this is the development of some blowouts with vegetation. So this is something we couldn't do with Dune Response Tool, but we've been trying to work towards these really complicated scenarios with the Aeolus model. And we've been doing lots of development on things like vegetation dynamics or sand fencing or multi-fraction sediment transport. We have a recent paper using the sand snap database with Aeolus, and embedding Aeolus with lots of different tools. And so one part of this work unit has been coupling Aeolus with the CMS model, and I think I'll talk more about that in the coming weeks at the CIRP IPR. But that's not why we're here today. We're going to focus instead on the Dune Response Tool, and hopefully I'll show you today some of the capabilities that we can get out of this tool. So if we do want another class of model meeting those objectives, we want it to be able to simulate dune growth from winds and also dune erodibility from high water levels and waves. Ideally, we would like it to be accurate, since that's quite important for the mission of the Corps of Engineers. Fast is really a key objective here, because we want something that can give us information over long timescales that can factor into some of these long-term planning assessments. In part, so maybe we can run lots of different simulations. And if we want a lower barrier to entry, ideally there's fewer site-specific parameterizations, fewer barriers to calibration, and it's easy to run. And if we can achieve all these things, then it can potentially be useful for hindcasting, for understanding what happened in the past, for forecasting, and as I'll show today, for probabilistic simulations as well. And you can see a link there. This tool is all open source and on the ERDIC GitHub in case anyone actually wants to use it. So going into what the model actually does here, I'm just going to sort of walk through general processes. Once again, it's not a process-based model in the traditional sense. It's mostly based on empiricism, although it is embedded in a cross-shore profile model. So there's lots of interesting things that we can do with the model. Fundamentally, a lot of what is in the tool is based on this concept of total water level. So here you can see the still water level, which is the combination of tides, storm surge, non-tidal residual, so something we'd measure at a tide gauge. And we have wave run up that runs up on the beach, and we would call that upper limit of the wave run up extent being the total water level. And this controls lots of things about what happens on the beach. If that total water level is low down on the beach, there's some exposed sediment, then there's the potential for wind-driven sediment transport. And this is might be conditions that you can recreate on the beach. As soon as that total water level exceeds the dune toe here, shown by that red marker, then typically what we'd expect is that there's volume losses from the dune. So based on our typical understanding, the number of waves impacting the dune face really drives the total volume of dune loss. There's a number of empirical equations that describe this relationship. And secondarily, as I mentioned before, if we do have some level of exposed beach, then wind, once it's over the threshold velocity, can also mobilize sediment and move that sediment into the dune. And so there's a volume also associated with that, the restorative force here from wind in terms of regrowing dunes. One thing that I'll note is in the original version of the model, we calculated this Q value, but we didn't really directly model or distribute that volumetric sediment that's shown by the delta V here. In terms of our profile, we just track the total sediment changes. So this is a recent addition. Now we're going to move towards a fully morphologically simulating model that includes both wind and wave-driven topographic changes. So Tanya mentioned before that there's a long history of this model. One thing that we had done was code all of this up in terms of a web tool or a web-capable tool. This is what's on the GitHub page in terms of not being able to just simulate these wind and wave-driven processes, but also dealing with all the sort of back end in terms of getting information, whether it was a hindcast mode or forecast mode. And these would be sort of typical outputs that would come out of the model. In a hindcast mode, you could predict, in this case, this was a dune retreat from a Hurricane Sandy type event. So all of this was fairly automated, meant to be pretty easy, has a morphological database, so you don't even need to go out and collect morphology data and put it into the model. Once again, meant to be pretty simple. Some limitations with the approach that we had done in past years was that mostly the wave and wind-driven processes are assumed to be independent, just the nature of part of this fast tool. And at the time, we didn't necessarily have data, so we didn't incorporate wind-driven topographic changes. And so these are going to be something that I'm going to advance on in the next couple slides. So what we did do is actually add deposition of these wind-driven sediment fluxes, as shown by this schematic, into the model. And I won't describe the rationale for all of this and data that was used to support this, but it's essentially a function of where vegetation is present, and also a length scale of sediment trapping, which also is primarily a function of the local vegetation properties. Other things that have been added to the model are adding in shoreline retreat. In this case, for the example application that I'm showing, everything is embedded in terms of a constant shoreline change rate. It can be positive or negative. But it turns out that including something about the beach morphodynamics is quite important for the dune. And lastly, we care a lot about sea level rise, and one thing that we wanted to move towards in our objective is being able to do long-term planning, and that in long-term planning efforts, we really need to account for the fact that the still water level offshore is changing. All right, so we have sort of the general framework for this tool. So I'm going to show an example of what outcomes of this look like when applied to a real world setting. So we're going to look at the Outer Banks, where there's quite a bit of data at the field research facility. I just want to point out here, there's a couple different panels. On panel B here is just shoreline change rates over the last couple decades. You can see that there's some reds, there's some blues, there's a mix of different colors. So there's a lot of variability, even over short spatial scale, what time average shoreline change rates look like. I think this is an important part of the story in terms of complexity of the local forcing conditions for dunes. And then on the right-hand side, you can just see some data from a USGS airborne LiDAR survey processed by the USGS showing local beach slopes and dune crest elevations and dune toe elevations. All of the histograms at the bottom are just showing histograms of all those parameters from those data sets. So you can see that over regional scale, in this case, this is across the whole town of Duck, that there's quite a bit of variability in all these morphometric parameters. And for the subsequent modeling, I'm primarily just going to use, at least any of the exploratory modeling I'm going to show, it's going to use all the mean parameters for the town of Duck. I guess before we do any exploratory simulations, I'll show that we can actually do some level of hindcasting at the site. So this is going to be a 2.5 year-ish simulation. You can see the bluish line now is the starting simulation. This is a prograding dune, and after that 2.5 years is the black line. And you're just going to see the time evolution of what this model is predicting in terms of dune growth at the site using real local winds, waves, and tidal conditions. And we can see overall that this final profile, matches relatively closely in terms of what we see in terms of both the patterns and total volume of changes of this dune that was on the FRF property. If we look at both data and the model, the data here is coming from some terrestrial LiDAR data that Kate's group had collected at these dunes. You can see that the model doesn't get all the details right. I would say most of the reason that there's deviations here is mostly just because there's a lot of three-dimensionality of the dunes here, and we're running a 1D model. But overall, it's tracking the time evolution of volume gains to the dune quite well without really much tuning, if at all. We did go through a calibration process using a genetic algorithm to actually tune the model to multiple profiles. You can see an example of that here, that the black lines, once again, they're showing some topo data from 2015, measured data in red, 2018. And now the calibrated model is shown in the yellowish color, showing that with two really different dune topographies, that the model with a single set of parameter values can do a pretty good job in terms of recreating what that topographic change looks like. And in this case, I said one of the goals was not having a lot of site-specific parameters. So our tuning parameters are shown in the bottom right-hand side. There's a length scale for aeolian deposition. There's an erodibility coefficient, a run-up coefficient, angle of repose, and things that weren't calibrated here, but you could in other applications are really just an aeolian transport coefficient. There's 2 or 3 other terms, but it's not really that many in the scheme of numerical models. All right, So what I showed is that we can do some hindcasting. The reality is that we can do this for any environmental time series. This was pretty easy to include any inputs into the model. And with that, we can really do deterministic simulations over a broad range of timescales. So that those hindcast cases I showed were for a period of, I think, 2.6 years. Those probably took about a minute to run. So just showing an example here with hypothetical data, 20 years might just take 1 or 2 minutes to run. And so that opens up different possibilities that we can also think about forecasting. We don't know what the environmental data is going to look like in the future, what the exact sequencing of waves and tides and wind conditions are going to look like. And so I'll talk in a minute about some clever approaches we've done to be able to emulate all of these forcing conditions. And if we're able to do this and run repeat simulations, then we can actually get to the point of doing probabilistic ensemble simulations in a Monte Carlo sense. So I'm going to describe this whole sort of secondary process in terms of forecasting to the goal of getting probabilistic simulations that relies on the fact that our individual deterministic simulations we have some confidence in. I think Dylan Anderson's on the line, so he can correct me when I say things wrong here. But a lot of Dylan's PhD work was on developing this Tesla framework, which really relies on the fact that a lot of local environmental oceanographic conditions are driven by large-scale sea level pressure fields, by regional weather patterns, and relatively large-scale processes. And so Dylan's approach, which is mostly statistical in nature, first focuses on using a stochastic climate generator to get to the point of developing a stochastic weather generator for local scale, where you can actually come up with downscaled wave and wind conditions. And so one thing that we've been doing together is actually adding in wind into this framework, so that at hourly scale we can predict wind direction and speed time series really at any site, which is critical for any of these dune growth models because winds are the main driver in terms of wind-driven sediment fluxes to the dune. It turns out being able to do this for waves and water levels is also important because the sequencing of wind conditions and wave and water level conditions is really quite important. And one nice thing about this framework is that it's stochastic in nature, so we don't necessarily get we don't just get one representation of future time series of all these environmental forcings. We can repeat, we can come up with multiple synthetic time series, so potentially thousands of them to iterate over all possible oceanographic and atmospheric forcing conditions. So an example of what time series coming out of this Tesla tool might look like are shown here. So we come up with significant wave height, the top, peak wave period, still water level, wind direction at hourly scale out to, in this case, it's 2100 or so. And if we plug this into the Dune Response Tool that we just showed, in the bottom panel, you can see a prediction of dune volume changes. So this would be a case where you see a positive number. So this is indicating that dune is expected to grow over time, relatively gradually. And we can also look at this in a profile sense. So this would be an example here where we're taking a Tesla time series, inputting it into the Dune Response Tool, and I'm showing an example where we have a stable shoreline. So as I said, we can vary what that shoreline looks like. In this case, it'd be a shoreline change rate of 0 that will stay fixed with time, and add an intermediate sea level rise curve. And if we do that, what we see here is that over this 100-year simulation, that a dune starts growing, in part because the still water levels are increasing because of intermittent sea level rise. You see sort of a gradual retreat of the dune, and it intermittently loses elevation and regains elevation. So the dune toe is not static in time. There's a lot of variability in terms of what the dune looks like. Not surprisingly, the Outer Banks is a pretty erosive system, and the mean shoreline change rate is just under about a -1 meters per year. I think it's 90 centimeters per year on average. So if we put this into the model instead and assume there's no shoreline stabilization, we get a really different result. So this is the exact same environmental forcings, still an intermediate sea level rise curve into the future, same wave, wind, tidal time series, just adding in a shoreline change rate. And all of a sudden we start seeing that the behavior in terms of the dunes is quite different, and the dunes getting knocked down and regularly regrowing as they retreat landward. So you could make out pretty well that the dune as an overall feature is retreating. One thing we could track is that dune toe elevation. So that's shown here for a number of different shoreline change scenarios and sea level rise scenarios. So just focusing on the yellowish colors first, the solid line is a stable shoreline with no sea level rise. You can see that it comes out to be a positive number, which means that the dune is actually prograding somewhat landward. This can happen in part because of avalanching on the dune. You can actually get a progradation of the dune. And when we add sea level rise into the mix, which is the dotted line that's still sort of yellowish, we basically get an overall stable shoreline that's not moving. So this is a trend basically for all these cases for different shoreline change rates, that adding in sea level rise makes the retreat slightly more. That's not too surprising. Other things we can pull out of the model are, now the top panel is dune crest elevation with time and beach slope variability. And you can see that these are also fairly time variable. So the dune crest, changes considerably for these deterministic simulations, depending on what the shoreline change rate is, depending on the sequencing of storms, depending on sea level rise. And the beach slope here tends to be quite variable with time as well, just a function of the dune toe location is variable, even if the shoreline is constant. The shoreline contour isn't changing at all in space. All right, so I already showed one deterministic simulation using one of these emulated climate time series out into the future. But one nice thing that we can do with this Tesla framework is roll the dice and get different sequencing of waves and wind properties. And so if we do that once again, we can get different chronologies in terms of what these conditions look like. And in the bottom, you can see that the implications for dune evolution have changed substantially. The trajectory, in this case, the dune volume change is still positive, so it's growing over time. But the timing of individual storms and the magnitude of erosional impacts here for the storms has changed. And we can do this over and over. And if we concatenate lots of different simulations, so in this case, we're going to do 1,000 different ones of these simulations, we can come up with a range of potential responses out into the future. And so the black line here is showing the mean volume change over 1,000 different simulations. You can see that it's positive. So along a stable shoreline, in this case with no sea level rise, we expect that a dune complex is going to grow. But you can see that the maximum potential response is about twice that of the mean. And there is a small potential that you have your dune lost because there are some negative numbers there as well. So a really wide range of responses, which is important to consider that, a single deterministic representation may not well represent the total range of potential responses into the future. As I noted before, we can also add sea level rise into this model, and it gives us realistic looking behavior in terms of what we would expect when we add in sea level rise. And you can see here that this essentially shifts all of the results downward. So our total dune volume, rather than being very progradation overall, is much closer to zero, and there's more cases that end up in the negative category. Not too surprising. If we instead look at cases where we allow for the shoreline to move at the rate that's measured in the data, the mean rate for duck that's measured in the data, not surprisingly, over time, what we expect is that the dunes lose volume, and we actually see that range of total responses starts getting smaller on these erosional cases, because things tend to be more driven by shoreline changes than by the sea level rise itself. So another thing we could sort of look at in terms of this lens is thinking about the time and likelihood of total dune volume loss. Here we're going to use the FEMA 540 rule, so actually tracking volumes that go below some volume to the point that they're not adding in sufficient buffering capacity. So on the left-hand side, if we look at a stable shoreline case, there's really one or two or just a couple of cases with no sea level rise where we have a totally destroyed dune. In this case, it's really just driven by some extremist storm event. And you can see that the total numbers in terms of how many dunes are lost, the count on the y-axis is much higher for when we include a negative shoreline change rate relative to a stable shoreline. This is not too surprising because we would typically expect that the dunes are much more persistent features on stable shorelines than on eroding shorelines. And on the right-hand side, you can start seeing that the histograms, so the gray bars versus the red bars, that the time at which there is a destruction of the dunes out into the future starts getting smaller when we add sea level rise into the mix. And so by this, I mean that if we build a dune tomorrow on the Outer Banks coastline, we might expect it to last, 30 or 40 years before it's being destroyed under modern sea level rise conditions. But as soon as we add in increases in eustatic sea level rise, that time to destruction might decrease by 5 to 10 years. So less protective services over time. So this is essentially the same data, just plotted in a different form and lots of different shoreline change rates added. The upper panel here is shoreline change rate versus this average time to going below the FEMA 540 rule with 100. All the numbers at 100 just mean that there was no destruction at all because that's the length of the simulation. So what we see is that as you increase shoreline changes, the duration at which that dune is expected to survive gets smaller. That's not too surprising. And on the bottom panel is just showing the actual probability that dunes are expected to survive under these different scenarios. So when we're dealing with really, really rapidly eroding shorelines, let's say -2 meters per year, there's basically 100% chance over the next century that those dunes are going to disappear. Whereas if we're on a stable or prograding shoreline, there's nearly 100% chance that those dunes are going to persist. And so the only times really on the stable shoreline cases where we have dune loss is really driven by extreme storms as simulated by Tesla. Everything is really shoreline dominated in terms of the response for pretty high shoreline change rates. And then there's this intermediate zone that you can see just with the background of white, where both individual storms and the shoreline change both make a pretty big difference in terms of the outcome of dunes and their likelihood to persist into the future. This is really just sort of harping on the sea level rise effect here. Now just adding in a couple more different sea level rise scenarios. All the black lines here are mean simulations. Once again, each one of these has 1,000 different simulations in them, forced by Tesla into the Dune Response Tool. And so if you look on the stable shoreline case, these really high numbers, so let's say, the mean value for no sea level rise is about 125 cubic meters per year 125 cubic meters. This is over 100 years. So it's saying on average, our dune is growing at about, 1.2 cubic meters per year. This is actually about the mean for the Outer Banks. And this is gradually going to get smaller and smaller depending on what future sea level rise trajectory we take. And if we look at the mean shoreline change rate, once again, sea level rise has a big effect in terms of those total volume losses. So the implications for this is that if we want dunes to be persistent on eroding shorelines in the future, we're probably going to have to add more and more sediment to these dunes to have them add the protective services that they're there to provide. So I think just a last set of simulations, add a little bit more material into the mix. I mentioned there's not a lot of free parameters in the model. One thing that we can do is change the erodibility of the dunes themselves when they're in the collision regime. And by the collision regime, I mean when the total water levels and wave runup are making impact to the dune face. And so on the left-hand side, just going to show the sort of baseline erodibility of the model. Erodibility coefficient that's used in the model, and then right-hand side is actually a reduced erodibility coefficient that could mimic, something like more biomass or some of the courier fiber, all of the things that Lee and Duncan and others test in the lab. And hopefully this plays. And I just want to make the point that, the internal mechanics of the dune can make a difference in terms of the long-term trajectory. So once again, all the same environmental forcings going into the model here. So the only difference here is the erodibility of the dune, and you can see on the right-hand side that the total retreat of the dune here is considerably less than the left-hand side, which is sort of typical dune sediments calibrated for the coefficient calibrated for duck from previous studies. So just thinking about some possible applications of the model that could be thought about sort of in R&D sense in the future. So hopefully I showed that there's, or at least I think there's some value to this reduced complexity Dune model. Show some skill against field data. It's pretty fast, and this demonstrates that we can or enables us to do long-term simulations and repeat simulations. From some of these early results, we see that there's a pretty tight coupling between what the beach response and the dune response is. The details of individual storms and the sequencing of events makes a pretty big difference on your outcome. So the range of response was quite large when we look out into the future, at least according to the model. And we're not always good about including sea level rise into our morphological models because it's a hard task, but it seems like the model is pretty stable here when we add sea level rise. So I think we're starting to think about what is that control in terms of both dune growth and erosion into the future. And then just sort of commenting on next steps, I think this Open Coast Physical Processes SFA via CODS, which really hasn't funded this model before. It's funded some of the Tesla work shown, but hasn't really funded the Dune Response Tool, is hopefully picking some of this up in FY25. And we have some military reimbursable funding, I think, through both the Air Force and the Navy for doing some applications. And working a little bit with folks from both Oregon State and University of Florida on this tool, thinking about capabilities for this long-term simulation and adding new capabilities. So with that, I will take any questions if people have them.